Have you ever wondered why your high-speed electronics sometimes act up, giving you weird glitches or data errors? It might be something called impedance mismatch. And if you see your signal reflecting back on an oscillator, in the world of electronics, signals don't just magically appear from point A to point B. They travel like waves moving through water. Every part of your circuit, every single trace on your PC, every cable you plug in, and every input on a chip has a characteristic called impedance. Think of it as the circuit's resistance to fast-changing electrical signals. It's not the same as simple DC resistance. It's a dynamic property that matters most when signals are switching rapidly. Now, here's where things get interesting. When a signal travels from one part of a circuit to another, say from a cable into a device, it expects the impedance to be consistent. But what happens if the impedance of the cable is 50 ohms and the input of the device is 75 ohms? That's an impedance mismatch. When the signal hits this boundary, it's like a wave hitting a wall. A portion of that signal's energy doesn't go through. Instead, it reflects back towards the source at very low speeds. Like in simple hobby projects, you might never even notice this reflection. The effects are too small to cause problems, but as you crank up the speed into the megahertz or gigahertz range, these reflections become disastrous. They can cause all sorts of chaos for your signal integrity. You'll see things like ringing, where the signal oscillates wildly before settling. You might get overshoot, where the voltage spikes way above its intended level. These distortions can lead to false logic levels, making a digital 1 look like a 0 or VCVRs, which ultimately results in corrupted data. So, how do engineers solve this? This is why you see termination resistors on high-speed digital lines. A termination resistor is carefully chosen to match the impedance of the transmission line. When the signal reaches the end of the line, instead of hitting an open circuit and bouncing back, it flows into the termination resistor. This resistor essentially absorbs the signal's energy, preventing reflections from ever happening. It provides a clear path for the signal to do its job without interference from its own echoes. It's a common misconception that impedance matching is all about transferring maximum power. While that's true in radio frequency applications, in digital electronics, it's all about maintaining signal integrity. We want the signal that arrives at the receiver to look exactly like the one that was sent. No reflections, no distortion, just a clean, reliable signal. Remember, if there's no match, there's no clean signal. It's a fundamental principle that keeps our modern high-speed world running smoothly. Thanks for watching, and stay sharp. Don't forget to like and subscribe for more insights.